In the last video, we looked at position time graphs, and now it's time to analyze the velocity time graph. And as I sit here on this beautiful Sunday morning, I realize I still don't really have my voice back, so hopefully you can bear with me through that. So here is a random velocity graph with various segments that we're going to analyze. And the first thing, just like we did with the position graph, is ask ourselves what information is obtained by reading the graph. And by reading the graph, we simply get the velocity. It's a velocity graph. And then we want to ask ourselves, well, what information is obtained from considering the slope? Slope, delta V over delta T. And we know what that is. We've already defined that as the definition of acceleration. So the slope gives us the acceleration. Consider the units for the slope. That's very telling. Meters per second over seconds. So that's meters per second squared. And then the area. Here's an area segment. Consider the units again. In one dimension, we have meters per second. That's this. In the horizontal, we have seconds. And so the seconds go away, and we're left with meters, which is a position, distance, or displacement term, unit, I should say. And so the real answer, however, is not any of those necessarily. It's specifically the displacement, how much the position has changed, not where it is necessarily. Okay, other considerations, the change in velocity. We start with V0. We go to V1 and V2. Between V1 and V2, we have delta V. So it's just a matter of taking 2 points, taking the difference, and we've got our delta V. Change in position. If you want to know the change in position, it's very strongly correlated to the displacement. It's not necessarily the same thing. We have the area, which is displacement. But to get the actual position, we need the initial position plus the area. So change in position is displacement. Position is initial plus displacement. And that initial position is not on the graph. It doesn't show on the graph. Other information would have to inform you about it. Now, how should you think about the velocity time graph? To get information about the acceleration, after answering the 2 questions, which are what kind of graph am I looking at, and what information can we get from reading it, slope, and area, just like we did before. So, consider that acceleration is slope, just like velocity was slope on the position graph. So, the key is the slope to get information about acceleration. So now you just have to ask yourself, well, is that slope positive? Is it slanted up to the right? Or is it negative, slanted down to the right? Well, if it's positive, it just means we have a positive acceleration. If it's negative, we have a negative acceleration. So let's consider those 2 possibilities and what other information will emerge from them as we look at the various possibilities. Keeping in mind that a positive slope corresponds to positive acceleration, negative slope corresponds to negative acceleration, consider the steepness of the velocity graph. So the slope, the value of the slope, which is the acceleration, what's it doing? So is it constant? Is the steepness constant? That means the acceleration, which is the slope, is uniform or constant. So the velocity is going up or it's going down uniformly, or it might be 0. Here's the possibilities. Positive, 0, negative slope, but they're all constant values of that slope. Now, what if it's getting steeper? That means the acceleration is increasing. So a steeper slope, looking like this. Obviously, the slope line anywhere along here as you progress along is getting larger and larger. The acceleration is increasing. What if it's getting less steep? If the plot is getting less steep, the slope is getting smaller and smaller, the acceleration is decreasing. So here's that reality. You look at this, the slope of this line is getting less steep. However, I want to show you this as well. Now here it's getting steeper. The slope is getting steeper, but it's getting more negative. So I'm going to call both of these acceleration. Well, I'm going to have to say becoming more negative. Because I can't just say the acceleration is decreasing. Unless in saying that, I really mean that the vector nature of it and its numerical character is that the number is getting more negative. Okay, that was kind of confusing. The acceleration is actually decreasing because we do have to consider whether it's positive or negative. You could say in this first one, it's getting more negative. This one, it's getting more negative. Now, of course, it was less positive. So the size, the magnitude of the acceleration is less here. Here, the magnitude of the acceleration is more. But in both cases, it's decreasing. So hopefully that makes a little sense. Move on. So you finish asking these questions. What can you now conclude about the nature of the acceleration from the answers to my questions? Well, let's consider the velocity graph, and let's plot this as an acceleration graph as well. So the first segment, we have positive acceleration, velocity going up. The next segment, constant velocity, no acceleration. Then velocity going down, or negative acceleration. So that was all easy. But segment 1, 2, and 3. Now what about this thing? There's actually a lot going on in this tiny little innocent looking segment of the graph. It's not so innocent. The acceleration of the slope of the line is increasing. The slope of the line is getting more positive. The acceleration, therefore, is getting more positive. You could say here it's getting less negative to 0 to more to greater positive numbers. So the numbers themselves are doing different things. But in the entire interval, the slope is becoming more positive, so we say that the acceleration is going up. So let's plot it. Plot the slope on the acceleration graph. First segment, keep in mind, these are all just conceptual, so I don't have any numbers, but whatever the value of this slope is, there it is. Then, that positive acceleration, the next segment, 0. No non-zero slope along here. Okay, so we have a is equal to 0, and then in this third segment, we have a negative slope, but it's pretty obvious it's less steep than this one over here. So I'm going to visually show this as not going down below the 0 point as much as the first segment was above the 0 point. So this is a bigger positive number than this smaller negative number. And now the last segment, after realizing that's negative acceleration. What's going on here? Keep in mind that at this point here, at the very bottom, the slope is 0. So actually, the value of the acceleration is going to be 0. It's going to cross the 0 point here. So basically, we have a lot changing with the acceleration, and it looks like this. And I probably don't have this proportional, but this little, in this interval of time, the same interval of time here, it goes through all this transition. The acceleration goes to 0 and then continues to increase. Notice nothing magical happens at acceleration is equal to 0. It just smoothly curves right through there. It just happens to be where it crosses the line. So the values of acceleration in time before this time are getting larger in number, but smaller in value because they're greater negative values. And after this time, larger number again, and actually increase in value. So we have acceleration going up, and that pretty well analyzes this whole entire velocity graph and shows you how it maps to an acceleration graph. Notice that the acceleration graph is simpler in concept to the velocity graph. Same thing happened with position to velocity. Velocity to acceleration, you're considering a more complex physical quantity, namely acceleration, but the graph itself looks simpler.